No wings, no spoilers, no active aerodynamic surfaces bolted to the body. And yet, at 300 kilometers per hour, this car stays planted to the road with more stability than most vehicles that look like they were designed in a wind tunnel. It weighs under 1,200 kilograms. It generates over 1,200 horsepower. And it was built not in Maranello, not in Stuttgart, not in Coventry, but in Wuhan, China, by an Wuhan, China, by an engineering team that almost nobody in the West has heard of. Here is what makes this genuinely interesting. The absence of wings on this car is not a styling choice. It is an engineering argument. A very specific claim that the way hypercars have managed aerodynamic downforce for the last 50 years is not just suboptimal, it is the wrong approach entirely. And the numbers suggest that argument is winning. If you enjoy deep dives into next-generation engineering and the shifting geography of where the world's most advanced machines are actually being built, hit like and subscribe so you never miss one. Now let's get into it. 50 years of the same recipe. To understand why this matters, you need to understand what European hypercar engineers have been doing since the mid-1970s, and why, for a long time, that approach made complete sense. The problem with a car traveling at extreme speed is not power. Power is relatively straightforward to manufacture. The problem is physics. At 250 kilometers per hour, the aerodynamic lift acting on a car body is roughly equivalent to trying to drive with someone steadily pulling the chassis upward. At 300 kilometers per hour, that lift force becomes severe enough to reduce tire contact patch pressure so dramatically that steering response degrades, lateral grip collapses, and the car becomes actively dangerous to drive. The solution that every major hypercar manufacturer converged on, Lamborghini, Ferrari, McLaren, Pagani, Koenigsegg, was to mount physical aerodynamic surfaces on the car. Wings, diffusers, dive planes, and active spoilers that could angle themselves dynamically in response to speed. The underlying logic was sound, generate enough downward aerodynamic force to counteract the lift, and the tires stay loaded, the car stays planted, and the driver stays alive. These systems work. The engineers who built them deserve real credit. The active rear wing on the Ferrari SF90 Stradale generates over 390 kilograms of downforce at 250 kilometers per hour. The Lamborghini Huracan STO uses a fixed rear wing that contributes to a total downforce figure of 420 kilograms at similar speeds. The McLaren Senna takes this further, with a full aerodynamic package generating 800 kilograms of downforce, more than the car's own weight at track speeds. That is a genuine engineering achievement. And for decades, it defined what a serious, credible hypercar looked like. But there is a ceiling built into this approach. And it is not a small one. Wings create drag. Every kilogram of downforce generated by a physical surface costs you in straight-line efficiency. The ratio varies by design, but broadly, the more aggressive the aerodynamic package, the more energy you spend pushing air out of the way at high speed. On a track, this is a trade-off engineers are willing to make. But on a public road, or in a class of vehicles where outright top speed and real-world range both matter, the trade-off becomes a genuine constraint. There is a second problem. Wings change the visual and functional profile of a car in ways that limit what the car can be. A vehicle wearing a 400mm rear wing cannot slip cleanly into a narrow parking structure. It cannot pass through certain automated car washes, and it sends a specific visual signal. This is a track car wearing road registration plates that many buyers in a new and rapidly expanding market segment simply do not want. For 50 years, the assumption baked into hypercar engineering was this: if you want the performance, you accept the wings. There is no other way to get the numbers. That assumption just got challenged in a way that is difficult to ignore. The car that rewrote the equation. The vehicle in question is the Aion Hyper GT SSR, produced by GAC Aion, the performance sub-brand of Guangzhou Automobile Group, one of China's largest state-backed automotive manufacturers. The SSR variant is the range-topping configuration, and the engineering decision at its center is the one that has been circulating in European motorsport forums for the past several months with a mixture of skepticism and genuine unease. GAC Aion's aerodynamics team did not build a bigger wing. They eliminated the wing entirely and replaced it with what they call an active underbody pressure management system. a proprietary configuration of shaped channels, electronically controlled flaps, and a Venturi effect floor geometry that generates downforce from beneath the car rather than above it. The principle is not new. Ground effect aerodynamics, using the floor of the car as a low-pressure zone that literally sucks the vehicle toward the road surface, was pioneered in Formula One in the late 1970s by Lotus designer Colin Chapman, whose ground effect Lotus 78 and 79 rewrote lap records at circuits across Europe. The concept was so powerful that Formula One banned it in 1983 because the downforce levels it generated were considered too extreme for driver safety at the speeds of the era. What is new is the application. Ground effect floors in production road cars have historically been difficult to implement because the geometry required to generate meaningful downforce is extremely sensitive to ride height. A Venturi channel that works perfectly at 100mm ride height can lose 60 to 70% of its effectiveness if the car pitches 20mm under braking or cornering. On a track car running a fixed low ride height, this is manageable. On a road car crossing a speed bump or navigating an uneven surface, it historically has not been. GAC Ion's engineers addressed this with an active suspension system that holds the underbody geometry within a 4mm tolerance band at speeds above 150 km per hour, regardless of road surface variation. The suspension reads road inputs at 1,000 times per second, a sampling rate previously seen only in Formula E and LMP1 endurance racing applications, and adjusts damper settings fast enough to maintain the floor geometry before the aerodynamic effect has time to decay. The result, according to the company's published test data, 680 kilograms of downforce at 250 kilometers per hour. No wing. No visible aerodynamic surface above the roofline. That figure sits between the Ferrari SF90 and the McLaren Senna. On a car that, from the outside, looks like a low-slung GT coupe, here's flip 1. The assumption was that ground effect technology could not be reliably deployed on a road car because ride height variation would make it inconsistent. GAC Aeon's engineers did not find a way around that problem. They solved it at the suspension level, and in doing so, they moved the aerodynamic constraint out of the bodywork department and into the software department, where it can be updated, tuned, and improved without touching a single physical surface. That is not a tweak to the old recipe. That is a different recipe entirely. The track doesn't lie. Published specs are one thing. Any manufacturer with a CAD suite and a marketing department can generate a downforce figure. What the engineering community actually watches for is real-world validation, independent testing, competitive deployment, and most importantly, the response of rival organizations who have no incentive to flatter a competitor. GAC Aeon did not release the Hyper GT SSR into a vacuum. They took it to Zhuhai International Circuit, a 4.3-kilometer permanent racing facility in Guangdong Province that has hosted rounds of the Asian Le Mans Series and the Blancpain GT Series Asia. Zhuhai is not a vanity track built to flatter a manufacturer's home product. It is a circuit with long, fast corners, turn 2 and turn 6 in particular, where lateral aerodynamic loading is sustained for long enough to expose any instability in a car's downforce delivery. The SSR completed a certified lap at Zhuhai in 1 minute, 38.4 seconds. For reference, the Porsche 911 GT3 RS, a car explicitly built for track use, wearing a full aerodynamic package including a massive fixed rear wing, laps Zhuhai in approximately 1 minute 41 seconds in comparable conditions. The Lamborghini Huracan STO, with its aggressive fixed wing and full race-oriented aero package, sits in a similar bracket. A wingless road car from a Chinese manufacturer that most European enthusiasts could not have named 18 months ago just posted a lap time that a Porsche 911 GT3 RS would need to work to match. Let that land for a moment. It is not just the lap time that matters. It is the data from the telemetry. GAC Aeon released lateral G-force traces from the Zhuhai run. Through turn 2, the long sweeping right-hander that loads the car for nearly 4 seconds at full speed, the SSR sustained 2.1 lateral G. That figure is consistent with what wing-equipped, track-focused machines generate through sustained high-speed corners. It is not what you expect from a car whose roof could be mistaken for a luxury grand tour. The suspension control system was holding the underbody geometry within its 4mm tolerance band through that entire corner, At 230 kilometers per hour, across 4 seconds of sustained lateral load, the active floor was generating its full 680 kilograms of downforce continuously, with no aerodynamic drop-off of the kind that passive systems experience when chassis geometry shifts under load. That is not a press release. That is a physics result. The decision signals that matter. There is a specific kind of signal that separates genuine industry disruption from well-produced marketing. It is not consumer enthusiasm. It is not social media coverage. It is the behavior of large, well-resourced organizations that have spent decades in the space being disrupted. Organizations that have no reason to react unless they believe the threat is real. 3 signals arrived within 8 months of the SSR's UI validation run. The first came from Porsche. In February 2025, Porsche's motorsport division quietly expanded its active underbody aerodynamics research program, reassigning 12 engineers from its GT road car development group into a new internal project focused specifically on ground effect floor geometry for road-going vehicles. Porsche did not announce this publicly. It emerged through a filing with Germany's Federal Employment Agency related to the reclassification of engineering roles at the Weissach Development Center. The timing was not coincidental. The second signal came from the FIA, the governing body of Formula One and the organization responsible for the technical regulations that shape what road car aerodynamics is legally permitted to reference. In March 2025, the FIA convened a working group to examine whether the active underbody suspension aero integration being deployed by Chinese manufacturers in the road car space required new regulatory language in the context of GT racing homologation. The concern was straightforward. If a road car's active floor system generates downforce figures that exceed those of purpose-built GT racing machines, the homologation category boundaries that GT racing is built on start to become meaningless. The FIA does not convene working groups over hypothetical problems. They convene them when a specific named product is forcing a regulatory conversation they did not anticipate having. The third signal came from McLaren Applied Technologies, the engineering consultancy arm that is separate from McLaren Automotive but draws on the same talent pool. McLaren Applied filed 2 patent applications in the United Kingdom in Q1 2025. Both relate to active ride height control systems, specifically designed to maintain underbody aerodynamic geometry within defined tolerance bands at road speeds. The applications cite prior art from Formula One ground effect regulations. Neither application names GAC Aeon. Both were filed within 6 months of the SSR's Zhuhai data becoming publicly available. Patent filings, engineering reassignments, and regulatory working groups, not press releases. Not product announcements. The kind of quiet, expensive, structural response that organizations make when they have concluded that a competitor has done something that cannot be dismissed. What 680 kilograms actually means for the rest of the world. Here is where the story expands beyond one car and one manufacturer. GAC Ion is not operating in isolation. The ground effect road car program that produced the SSR was partially funded through a research partnership with the Hunan University School of Mechanical and Vehicle Engineering, which has been running active underbody aerodynamic simulation programs since 2019. The active suspension control system, the component that makes the entire approach viable on public roads, was developed in collaboration with Huawei's Intelligent Automotive Solutions division, which has been embedding itself into Chinese vehicle development programs across more than 40 manufacturers since 2021. This is the structural point that changes the scale of the story. When Lotus built the ground effect Lotus 78 in 1977, that technology lived inside one team. It spread to competitors through the normal process of engineers moving between organizations, taking their knowledge with them. That process took years. The active suspension aero integration that GAC Aeon deployed in the SSR is built on a software and sensor architecture that Huawei has already embedded across a significant portion of China's automotive manufacturing ecosystem. AITO, Series, BAIC, Chery, and several other Chinese manufacturers are already running Huawei's HarmonyOS intelligent driving stack in their production vehicles. The core sensor fusion and real-time chassis response algorithms that make the SSR's floor control system viable are not proprietary to GAC Aeon. They are modular components in a shared development platform. That means the barrier to the next Chinese manufacturer deploying similar active underbody aerodynamics is not a decade of original research. It is a licensing conversation and an integration program. Scale that across an industry. Europe took roughly 15 years to move active aerodynamic wings from Formula One into road cars after the technology was proven at race level. The Chinese automotive ecosystem, running on shared software infrastructure, could replicate that diffusion in a fraction of the time. Here is the scale math payoff. If even 4 Chinese performance manufacturers deploy functional active ground effect systems across their product lines within the next 5 years, a conservative number given the infrastructure already in place, the segment of the global hypercar and performance GT market that is currently defined by European wing-equipped designs will be facing competition from vehicles that are aerodynamically equivalent, visually cleaner, and manufactured at a cost structure that European low-volume producers structurally cannot match. Ferrari produces approximately 14,000 cars per year. GAC Group, the parent company behind GAC, has annual production capacity exceeding 1 million vehicles. The cost per unit economics of developing and deploying advanced suspension control software across a 1 million unit base are categorically different from developing it across 14,000. This is Flip 2. The story was supposed to be about one interesting Chinese car with a clever aerodynamic approach, but the deeper look reveals something more permanent. The competitive moat that European hypercar manufacturers have relied on, the assumption that the engineering capability required to do what they do is concentrated in a small number of organizations in a small number of European cities, is no longer structurally secure. The capability is moving, and it is moving on infrastructure that is already built. The obstacles are real, so is the momentum. None of this means the transition is frictionless. There are genuine obstacles that deserve honest acknowledgement. GAC Ion's published downforce figures have not yet been independently verified by a third-party aerodynamics lab with full access to the car's underbody geometry and sensor data. The Zhuhai lap time is certified by the circuit's timing system, but the specific claim that the floor system was operating at full effectiveness throughout the lap rather than at peak effectiveness in specific corners has not been externally audited. The active suspension system that holds the underbody geometry also adds mass and mechanical complexity that carries long-term reliability implications. In a track environment where a car might complete 50 or 60 high-speed laps in a weekend, the system's ability to maintain its 1,000 samples per second response rate without thermal degradation or sensor drift has not been demonstrated over a sustained endurance period comparable to what European manufacturers put their systems through during development validation. And the commercial question remains open. GAC Aeon has announced a production run for the SSR without publicly committing to firm delivery timelines or confirmed pricing outside the Chinese domestic market. European and North American homologation, the regulatory certification required to legally sell and drive a performance vehicle on public roads in those markets, is a process that has delayed Chinese manufacturers before. These are not trivial concerns. They are the legitimate reasons why engineering teams at established European manufacturers are watching carefully rather than panicking publicly. But watching carefully is itself the tell. 5 years ago, the European hypercar engineering community was not watching Chinese manufacturers carefully. They were not watching them at all. That changed. And the specific mechanism that changed it, a wingless car from Wuhan posting lap times that a Porsche GT3 RS needs to work to match, is now sitting in the institutional memory of every major European performance manufacturer's competitive intelligence function. The window for dismissing this as a regional curiosity has already closed.